Hello and welcome. This presentation introduces a method for enhancing monocular 3D hand reconstruction using learned texture priors. Texture in 3D hand reconstruction is usually treated as post-processing component. Yet monocular reconstruction is inherently ill-posed, requiring depth and articulation to be inferred from partial, often occluded observations. State-of-the-art methods remain largely geometry-driven, underutilizing the dense photometric signal in the RGB image. This motivates a key question: can texture be elevated from appearance to a dense, spatially grounded supervisory signal for improving geometric reconstruction? Current monocular 3D hand reconstruction relies mostly on geometry, regressing manoparameters through sparse losses. On the other hand, texture models prioritize realism over accuracy. This approach bridges this gap, introducing a learned texture prior that enables dense alignment, transforming texture from a mere visual detail into a powerful supervisory signal. This work introduces a learned texture model, trained end-to-end in a self-supervised manner. The model receives sparse and partial texture observations and reconstructs a dense, coherent UV map using an attention-based architecture. Importantly, the model does not rely on ground truth texture annotations on training. Operating directly in UV space enables seamless integration as a plug-and-play module within existing 3D hand reconstruction pipelines. Before introducing the texture module, it is useful to clarify the underlying representation. The texture module is learned in a canonical UV domain, enabling dense reasoning directly on the mesh surface. This requires a parametric hand model and a consistent UV mapping. Here, Mano provides the differentiable geometry, and HTML defines the canonical UV layout, assigning consistent surface coordinates to every vertex. This forms a stable foundation for learning the texture prior, while remaining adaptable to other geometric representations. From the input image, a partial texture corresponding to the visible hand regions is projected into the canonical UV space. This UV map is inherently incomplete and often noisy due to occlusions and pose ambiguities. From these correspondences, RGB appearance features are extracted and combined with random Fourier features in UV space. These features are concatenated to create a rich representation of the visible hand surface and its spatial coordinates. The concatenated features are then processed by a transformer architecture that models long-range dependencies across the UV space. After the transformer, a convolutional upsampling decoder reconstructs the full, coherent hand texture. During training, supervision is derived from incomplete, sparsely observed textures from input images, mapping incomplete textures to a common canonical UV space, enabling spatial alignment across the dataset. The enhanced Hamer is trained end-to-end using both geometric and photometric supervision. Geometric losses constrain pose and mesh predictions, while photometric consistency is enforced through differentiable rendering of the textured hand. This allows appearance cues to directly supervise the geometry during training. Quantitative evaluation assesses the impact of learned texture priors on hint dataset. Our method improves performance across most PCK thresholds and remains near parity in the rest, indicating that texture priors enhance reconstruction robustness. On freehand, we remain competitive with state-of-the-art methods. This confirms that the texture module integrates seamlessly and provides additional supervision without degrading reconstruction quality. On HO3D, stable performance is maintained relative to the baseline. Pose and surface metrics remain competitive, indicating that the incorporation of texture priors does not compromise geometric reconstruction. Enhanced Hamer reaches performance comparable to Hamba. Importantly, these gains are achieved without modifying the backbone, unlike Hamba, which improves geometry through increased architectural complexity. This shows that a learned texture prior can elevate existing reconstruction systems without redesigning the base network or increasing its computational footprint. Qualitatively, the reconstructed geometry remains stable across occlusions and extreme poses. Minor geometric corrections in image space drive significant 3D alignment gains, particularly in articulated regions like the fingertips, resulting in tighter mesh placement and reduced geometric ambiguity. In the wild, the enhanced Hamer produces consistent geometric predictions from sparse inputs, improving robustness rather than overfitting to individual samples. In summary, the texture module is self-supervised, plug-and-play, and backbone-agnostic. The module enables photometric supervision that improves 3D alignment and can generalize to any UV parameterized mesh. Thank you for watching this video.